You did lots and lots of studies like this, each time calculating the odds ratio from these studies. What you'd end up with is not one odds ratio, but many odds ratios from these many different studies. And now you could draw a histogram from those many odds ratios. You could calculate the mean, you could calculate the variance of those many odds ratios. That's what the sampling distribution refers to as those many different numbers you would get. You did many, many studies, like the one study that you actually just did. Well, it turns out from statistical theory that if you looked at many studies like the one you just did and took the log of those odds ratios, and you looked at the distribution of those log odds ratios from those many studies, you'd see something which follows what is known as a normal distribution. The average of all those many log odds ratios is estimated by the log odds ratio from the one study you just did. And the standard deviation of all those log odds ratios from all those different studies is given by this following formula. From the one study you did, you'll have a number in the A cell, the B cell, the C cell, and the D cell. This here. You take 1 over A, 1 over B, 1 over C, 1 over D, add them up, you take the square root of that, that's what raise it to the 0.5 power mean, and that would give you what you'd expect for the standard deviation of those numbers. And statistical theory says that if you have a distribution that's normally distributed, that there's a 95% chance that the true log odds ratio will fall between the log odds ratio you observe in your one study after you subtract 1.96 times standard error from it, and take that same log odds ratio from your study and add 1.96 standard error units to it. Meaning, to show you by an example, here's a 2x2 table from SAS, not using the survey you just did. This is a study I did looking at the relationship between males versus females. Males are the ones and females are the zeros. It came into the emergency room with chest pain, and looking at whether those people were admitted, that's the first column, or not admitted. So of 380 men, 60% of them were admitted. 404 women, 45% of them were admitted. Odds ratio you get from that table would be 1.79. The confidence interval we get from that SAS printout goes from 1.35 to 2.8. So how did we get this confidence interval from this 2x2 table? What is SAS doing? Basically what it does is it calculates your odds ratio. Go back to the table. Remember, the odds ratio is 228 times 220 divided by 152 divided by 184. It then takes the log of that number, gets a log of 1.79, which is equal to 0.58. It also calculates from that 2x2 table the standard error for that log odds ratio. 1 over 228 plus 1 over 152 plus 1 over 184 plus 1 over 220, adds them together and takes the square root of that, raises it to the 0.5 power and gets 0.1444. So what SAS is doing is using that normal distribution theory, says if you take your odds to it, 1.96 standard error units, you'll get a confidence interval, a 95% confidence interval for true value for the log odds ratio. Meaning there's a 95% probability that this process would give you an interval that contains the true log odds ratio. Well, you want an odds ratio. Your odds ratio is 1.79. To get a confidence interval around your odds ratio, you take the confidence interval around the log odds ratio and change its limits from the log scale to the odds ratio scale. So e to the 0.3055. Interval, the 95% confidence interval for the log odds ratio. So this whole idea of building confidence interval is built on theory. Theory that a particular measure of association, logarithm of the odds ratio you get from your one study, would have a normally distributed sampling distribution with a standard error that could be estimated by the formula we used on the previous slide, this formula here. Well, to give you an idea that's true, what I did is I did something called bootstrapping. What bootstrapping allows you to do is from your one data set to generate other data sets that could look like other studies you would do on the same people. Essentially, I developed another 1,000 studies. Each of these other 1,000 studies contain people just like the people I had in my data set, contains 784 people just like the one I had in my one data set. We'll talk about bootstrapping later, probably in a few weeks from now. But just for the time being, just think of it as a way to try to generate other studies using people just like the people you had in your one study, using studies which are the same size as the study you just did. Well, if I did this 1,000 times, and each time I calculated an odds ratio, each time I calculate the log of the odds ratio, on average, the average of those 1,000 log odds ratios from those 1,000 similar studies is 0.5836. Very similar to the one odds ratio, the log of the one odds ratio I got from my study. And more importantly, the standard deviation is 0.1409 when I looked at the standard deviation of those 1,000 log odds ratio values from those 1,000 different studies. And notice 1.1409 is very similar to what the statistical theory suggests it should be, is 0.1447. And also, if I look at those 1,000 log odds ratios, here's a stem and leaf diagram, which is like a histogram on its side. Notice it looks like a bell-shaped normal curve. So statistical theory is supported by these computer simulations. The sampling distribution does look normally distributed, and the standard deviation of this sampling distribution is approximated by that formula which SAS uses to build its confidence intervals. So what if we build the confidence intervals from year one study, looking at spam consumption and needing a vacation? The odds ratio from that study would be 0.55. The confidence interval goes from 0.09 up to 3.14, a very wide confidence interval, suggesting that people who eat spam have a lower odds of needing a vacation now, as low as 0.09 compared to the non-spam eaters, but also it's consistent with very high values, 3 times as likely to need a vacation right now. The fact that this confidence interval is so wide contains measures of association that are less than 1, contains the value 1 itself, and also contains values far from 1 in a positive direction, is a reflection of how much information we have in this study. We only had 21 people in the study. Not a very informative study, and that's why this confidence interval is so wide. So that's how you build confidence intervals from 2x2 tables. So there's a relationship you might gather now between confidence intervals and tests of significance. If the null hypothesis, if the null value, in other words, risk ratio equal to 1, odds ratio equal to 1, is contained in the 95% confidence interval, that means the data supports the null hypothesis. That means your p-value was bigger than 0.05. So if we go back to the previous slide, here's your 95% confidence interval for your odds ratio going from 0.09 up to 3.14. Notice inside this confidence interval is the number 1.0. It's one of the numbers that are supported by these data. One of the numbers for the true odds ratio for which these data support. Therefore, these data support the null hypothesis, and therefore your p-value should be bigger than 0.05. And we saw that when we looked at the 2x2 table. Give me the p-value. Let me see if I go back.